All right. Welcome, everybody, to the workshop provided by Material Gene Foundation. My name is Zi-Kui. I would like to first introduce our three presenters for today and tomorrow. I think we start with Dong Wanxin, please.
Hello, everyone. My name is Dong Wanxin from Oak Ridge National Laboratory. My research background is computational thermodynamic modeling approach. I learned from the best, and then density functional theory. And recently, I got interested in machine learning, and I'm going to share my experience with you today. Thank you.
Thank you, Dong Wang. Richard?
Hello, everyone. My name is Richard Otis. I have a PhD in material science and engineering and computational metallurgy from Penn State. I'm a director of the Materials Genome Foundation and creator and co-lead of the PyCalFed computational thermodynamics package that you're going to hear about during this workshop.
Thanks, Richard. Brandon?
Hello, I'm Brandon Bachland. I'm also a PhD graduate from Penn State. I'm currently working at Lawrence Livermore National Lab, but I'm here today as a board member of the Materials Genome Foundation. I'm a co-lead for the PyCalFed project and the lead for the SBA project.
Thank you very much, Brandon. Okay, as you see from the agenda, Richard sent to you. So I'm going to first present an introduction of Materials Genome Foundation and some about the CalFed modeling and the tool development. And then we have Dong Wang about Ascens, talk about Ascens program. And then Richard will be PyCalFed, Brandon will be SBA. And in the future, we have a number of other programs in the pipeline we're going to add into the portfolio of the workshops. Let me share my screen. Again, my name is Zi-Kui. I'm a professor at Pennsylvania State University. I'm also a co-founder of the Material Genome Foundation, together with Richard Otis, and Brandon now is also a director of the Material Genome Foundation. Okay, the Material Genome Foundation was incorporated in 2018 in Pennsylvania, a nonprofit organization. The goals of the foundations are to promote computational approaches in science and engineering, support the development of computational tools and databases. Our current actions, including organized workshops, this is one of them, and provide the cloud-based service for your workshops. For example, you have your programs and would like to provide to the communities through a cloud-based service, we can do that. And we are also in the process of developing open source ecosystem for material science. We call it OSMATs. And I'm going to talk a little bit about the more general about materials, then how it connects to what we are doing today. Is the materials and civilization. As all of you know that many years ago, started with Stone Age, Bronze Age, and the Iron Age, and with the last two made by human-made materials. And then after that one, we get industry 1.0 to 3.0 in terms of steam power, electricity, and computerization. And I know that we're now in the industry manufacturing materials 4.0. It's about a digitization. So digitization is really the digitization of knowledge. And what it basically means is that in terms of manufacturing, it's basically how you process materials to form products and the properties of materials which are closely related to phases, individual phases we have. So if terminology of phase stability and functionality, you probably learned that thermodynamics by Gibbs back in 1870s, and 100 years later, we had the digitization of thermodynamics pioneered by Larry Kaufman in terms of CalFed method. And 50 years later, 2020, nowadays CalFed-based material design is widely used in major industry companies and by research institutions. We'll talk about next 50 years would be, and I hope what we are talking about today would serve the purpose for the next 50 years. Okay, if if you have taken thermodynamics, you probably heard that thermodynamics is for equilibrium, but is that really true? If you look at first law, it's not. First law does not specify the system must be in equilibrium. But if you look at the Gibbs thermodynamics, yes, it is, because in this equation, it's for equilibrium only. So what's the difference between the first two equations here is that is the second law. Second law is basically talk about entropy production in terms of internal processes and entropy reduction. So if you add this term, then it's not for equilibrium only, it's for non-equilibrium. So if you use the Gibbs energy for non-equilibrium system, you have to add this entropy reduction. So now you see that Gibbs energy must be a function of temperature, pressure, composition, and the internal degree of freedom. So that's what CAFAD does. CAFAD models Gibbs energy of individual phases as a function of temperature, pressure, composition, and internal degree of freedom. Okay, so the COSI is the internal state variables. So for example, we can give some examples of internal variables. For example, non-stable crystal structures, BCC copper, for example, in the BC solution of iron and copper, which you have been both theoretically studied and experimentally measured. And the ordering between in complex phases, polarizations, like magnetic spin, electrical dipole configurations, and then all kind of defects are internal degree of freedom because they are not fully in equilibrium. Okay, so what CAFAD is that is really model the free energy as a function of those internal variables. And so you can model free energy and its derivatives, and also you can model mobility because that's also energy, right? You can do other properties, and even more, you can do the interfaces between the phases too, in addition to individual phases. And we have the CAFAD community, in case some of you are not familiar. If you go to www.cafad.org, you can see that we have an annual conference. It's the Golden Conference style since 1973. Next year, we can celebrate the 50th anniversary. If you want to organize, as you can see, it's planned a decade ahead. For example, Richard is going to organize one in 10 years. And then we have a foundation, which is support scholarships and awards. So I see that there are many students in today's workshop. If you come to CAFAD meeting, we provide scholarships. Our goal is to provide scholarships for all students attending CAFAD meetings in the future. That will include the accommodation and the food for a whole week. And we also have a journal since 1977. To do all this work, we need databases and the tools. And if you look at the CAFAD Journal, Volume 26, Issue 2, we have some tools and discuss there. We have commercial tools because that's what the industry needs. They need commercial tools, right? It has good support. Thermocalc, FactStage, CompuSum, Pandat, GMAT Pro, Matacac, and they are widely used in industry. I was told that Thermocalc has more than 1,000 users, active users. And we also have open source codes like OpenCAFAD, Thermochemica, and PyCAFAD aspect. So that'll be a focus of our discussing these 2 days. And it has some features, particularly the high throughput modeling and with uncertainty quantifications. And the CAFAD modeling, one slide to talk about a little bit more is this free energy function. And then we input the data, we included the derivatives of free energy and also the equilibrium. And it starts with pure elements, binary, ternary, and multi-component system. After you build up the database or databases, then you can do the material design. You can do equilibrium, you can do driving force, physical chemical properties through the first and second derivatives, and we call this material genome. Okay. And the reason we have to do this one is because this from Richard's thesis that before we had a one-way traffic, so it's very difficult to revise the database. Okay, that's one example. Shows that if you change C here in a 6-component system, you have to change so many systems simultaneously in order to maintain the integrity of this 6-component system, which were not possible until PyCAFAD SBase are developed. Okay, so in addition to PyCAFAD SBase, we have more tools, which is first the data generation. We have DFT, we have machine learning, and we have experiment data compiled. And then we have data processing. That's the new one, the PACAF SBA. And then we have the Material Genome Foundation, which is host a workshop. This one is you're attending today. Then we have other one next one coming October. And the one after that will be next spring in San Diego before the TMS meeting. So MGF Actions, as I mentioned, we have in addition to the workshop, we have this open source ecosystem. I want to particularly mention that Ascends, which is going to be presented by Dongwan Xin today, is one of our efforts to go beyond what developed at Penn State. So you can see here we have the MGF, we talk about from the Penn State, then we want to take all the community tools into the package. Okay, so all the tools can talk to each other, share the data. Okay. And we want to work in the format of the Cloud Native Computing Foundation. In case you're not familiar, you will see this is a fantastic concept to connect the community tools together and data. And we want to provide a cloud-based service. For example, you can see how this workshop works today. And if you want to have your tool be organized the same way, which we can help. So you only need to prepare your tool, just like Ascends. As you will see today, Dongwan has his codes, his examples, and then we can package it and present in this cloud-based way. So it's very easy for people to access, which Dongwan doesn't need to worry about at all. Okay, so if we can do this, since then we have this data ecosystem. I want to emphasize again that you have the photo data, basically it's the data for the modeling, and then take a pack of SBA to build up the process data. We call it CAVA databases. Then you do the manufacturing and the service, you get new data, you get a cycle back into the database, then into the materials recycle, you can get back to the database. So this is really the system which continuously improves the database. At the moment, we can see PACAF SBA are the only tools who can do that. Okay, so that's my last slide. We call this approach, this framework, ocean of data. It's basically integrating first principle calculation and kind of modeling with machine learning. And if you want to know what application we can do, there's another paper I wrote 2 years ago about computation, some of the dynamics and its applications. And I just finished another paper. It's about even broader applications. Beyond the typical application we use. For that one, I want to emphasize again, we have this ocean of data concept. PACAF and SBA are the enablers to connect all the existing databases and generate new data for material design. We hope we get this kind of a cycle in place. Okay, I think that's all I have. Again, I want to thank you for participating at this workshop. I hope you have a great time, and we hope to hear your comments. As you see, this is very interactive. If any questions, comments, you can ask it. You can just unmute yourself and ask questions, or put your comments in the chat area, so people will answer those questions. All right, and then maybe I first ask if you have any question to me. Okay, if it's not, I will pass the podium to Dongwan, so he can start to talk about his machine learning code Ascends.
All right.
Thank you very much.
Thank you. Can you see my screen?
Yes.
All right, ready to go. Okay, so let me quickly
just 1 second, Dongwan. I'm
Sure.
going to stop this recording and start a new recording.
Sure.
So we don't have to do this. I stop the recording now.